This is Statistics 243 at Berkeley for Friday, November 7th. Okay, let's go ahead and get started. So I just wanted to say a few more words on the linear algebra material. So I want to come back around to a couple points about how we would take some linear algebra that we want to implement on a computer and actually do it in an efficient manner. So we've seen a whole bunch of strategies that we can use, that the order of operations matters. We've seen that the algorithm that you choose matters. We've seen that you don't necessarily execute the linear algebra in the exact form that it's written, that you would write it mathematically. For example, when we're solving systems of equations. We've also seen this idea that if you have an expression, if you have one expression but you know where the pieces of that expression came from, there may be a way to do it more efficiently by going back to the original pieces. So we had that example of suppose that I was doing Q times X. This was from when I was doing the householder reflections problem. And I said, well, we could think if we had Q, we could do this. But if we know where Q comes from, if we know that Q is in that case I minus 2 U transpose, where these are vectors, then I can sort of go a step backwards and say, well, this is Q. It has a special structure. The structure comes from me knowing how I created it. And I'm going to be able to write this in a much more efficient way than to directly do this. Another example of that, which I won't go through in any detail, is this notion of something called a low-rank update. So there might be times where you have a matrix that is formed like this. So this is a full matrix, and this is an outer product of two vectors. And it turns out that if you have that, where that's either an outer product of two vectors, or you might have an outer product of two matrices, they're n by m, that the inverse of this A tilde, which has this special structure, is known to have this form. And the nice thing about having this form is instead of inverting an n by n matrix, it turns out you have to deal with inverting an m by m matrix, where m might be a lot smaller than n. So again, I don't want to go through the details of where this would come up or of implementing it, but just another example of if you know the structure of the matrix and that matrix is formed from other pieces, there are often times that you can use a more efficient algorithm or a more efficient set of operations to do the computation you need. Okay, the other thing I wanted to mention was sparse matrices. So suppose that not necessarily that we know how the matrix was formed from pieces, but what we know is that we have a matrix and it has a lot of zeros in it, so it's sparse. So if that's the case, then it's well known that we can often implement things much more efficiently by taking account of the zeros and not actually doing any of the computations with the zeros that we know are just going to give us back. Either if we multiply, we're obviously going to get a zero. If we add, we're just going to get back the same value that we put in, et cetera, et cetera. So there are basically packages for R. There are packages for lots of different pieces of software that will work with sparse matrices. You can do that in MATLAB. I'm sure there are sparse matrix routines in Python. There are various C libraries that will implement various matrix operations, including matrix factorizations, when the input matrix is sparse. And so in R, a couple of the packages that are useful are these ones that I've listed here. So I thought we could just talk a little bit about what does it look like when you actually store a matrix in the sparse format, and how would you actually write up some code? Right? How would you actually code up, say, a matrix vector multiplication in that case? So here's an example. Suppose we have this matrix here, which I must have had some reason why I decided I wanted to use powers of things that were divisible, that were in base 10, 10 to certain powers, but I don't remember why. If I want to think about storing this in a way that I could basically recreate this matrix, but without storing all of the zeros, there are a variety of different ways that you could go ahead and do that. Can someone suggest one way? It doesn't have to be the best way, but just one way that you could encode this matrix without storing all the zeros?
The vector that tracks the position of non-zero elements, and then you have a vector that contains those non-zero elements.
Okay, so if the vector containing the non-zero elements, presumably it's going to depend on whether I might want to store them by column order or by row order. I'm not storing by row order here because that's what we're going to see in this implementation here in a second. So I would store the 1, and then the 10, and then the 100, and then the 1,000. And then how are you thinking of storing the information about the positions?
A single number treating the entire matrix as a row array.
Okay, so you're saying, well, I would then store a vector that was 3, comma 5, comma 9, etc. Okay, so that would be one way to do it. Other thoughts on what I could do here? Okay, so this would be storing the sort of positions as a single vector. I could also store a vector of the row indices and a vector of the column indices for each of the elements, right? So this would then become the row position would be 1, 1, 2, 4, and the column position would be 3, comma 4, comma, what am I missing? Oh, 3, comma 5, sorry. 3, comma 5, comma 4, comma 1. So there are a variety of different ways that you could think of doing this. We're going to see yet a third one in a second. But all of these you can see if we have a lot of zeros. In Daniel's case, we were only going to store actually 5 numbers here instead of storing the 25 numbers there. In this case, we're only going to store, wait, did I get that right? 1, 2, 3, no, 8 numbers. In this case, we're going to store 12 numbers. But either way, you can imagine if the proportion of zeros gets larger, then the savings is going to get even larger than that. So if we actually looked at the spam package in R, what we'll see is something slightly different than what we just did there. And it's called a compressed sparse row format, or CSR. So where is it here? Okay, so another reason I wanted to show this was because we'll see a little bit of S4 object-oriented syntax from R. Okay, so all I'm doing here is I'm first creating the matrix R as a dense matrix in the sense that I'm explicitly including the zeros. And then I'm going to convert it to the sparse matrix format using this as.spam function. So once I do that, this mat object is now a sparse matrix object. You can see that because that's what its class is. I think if it were a lot larger than this, it might not print out all of this, although I don't remember off the top of my head. But the other neat thing is this is an S4 object, and so we can look into the fields of the S4 object with the @ symbol as if instead of the $sign, since this is S4 instead of S3. And so what you'll see is that what you could see is that the elements of this spam object are the entries, which is exactly the first vector over there. And then the column indices, which is exactly one of those vectors over there, saying what's the column position of each of the values. And then something slightly different, which is something called row pointers. So if we look and see what those look like, this is exactly the same matrix. You can see these elements are the same. You can see the column indices are the same. But that if we wanted to know what the row pointers are, it's basically telling us, this is basically telling us the position of where in this vector does each of the rows, the non-zero elements of a row, start? So the first value is, so if I want to find the first non-zero value in the first row, let's see, no, I'm not getting this right. It's the reverse of that. If I let's see, how does this work? If I want to know, okay, so the first, sorry, I'm getting confused because this 1 here is in the third position, but it's in the first row. If I want to know where the first row starts, it's going to be the first non-zero element, so it's going to be this guy. If I want to know where the second row starts, so the second position in row pointers here, that's going to be the third non-zero element, so that's going to be the 100 value. And if I want to know where the third row starts, well, that one's all zeros, so sort of by default the convention is that this is going to be the fourth value, but then you repeat the 4 here because actually the fourth row the first non-zero element there is going to be the fourth value in this set of non-zero elements. So one aspect of this is going to have as many elements as there are rows. So there may be cases where it's a more efficient storage than some of the other approaches there. Huh? Did I get it wrong? Okay. Huh?
There are only 4 rows here.
Yeah, there are only 4 rows. There's just I've never sort of gone back and dug into the convention, but by convention, you put in the value for what would be the next row, which doesn't actually exist. There's probably a reason for that, but I don't actually know what it is off the top of my head. Is that why, Monica, why you were complaining? You were about to complain as well? Okay, good. Other questions? A very fair question. Okay, so let's see. So this could potentially be more efficient than some of those, and some depending on the sparsity pattern and the proportion of non-zeros, it may or may not be more efficient. But I think if we look at an example of coding up how you would do a matrix vector multiply with this, yeah, Eugene.
Is span an R notation, or is it just called the C?
It is calling Fortran code behind the scenes, yeah. So if we looked at the implementation of, if I were to basically write this out in R code, but you could imagine this would just be a C or a Fortran routine. If I wanted to multiply the matrix A times a vector B, and I operate row by row, that's going to sort of naturally fit with this idea of having these row pointers. So I'm going to loop over the rows. It would be a good idea, I didn't actually put it in here to check to make sure the row is not empty, but that is not all zeros. But for the moment, let's assume that it's not. And I'm going to have an accumulator x, which is basically going to be the value for the resulting x vector. That's the result of doing this multiplication. So I can use this row pointer vector in a nice way here. I can basically loop from row pointer for that row to the row pointer for the next row minus 1, and that'll basically tell us the indices that correspond to that row, the indices of the elements in this vector that correspond to that row. And then that's going to sequentially be the j value, and then I can pull out that j value, and I can also pull out the column index corresponding to that j value, and that'll tell me which element of B I'm going to multiply the value by. So this particular way of storing things works out quite nicely in terms of writing the code to then do something like a matrix vector multiplication. And you could work out how many operations you would have to do here, and it's basically going to scale with the number of non-zero elements in the matrix. Okay, so any questions at this point? Yeah.
Is this like sparse representation? Is that sort of like the motivation for like NoSQL story? Like where it's like instead of like doing row based or doing column based, because like gives some data on NAs, so you just like it's kind of random.
Yeah, I don't actually know because I'm not really very familiar with NoSQL stuff, so I'm going to punt on that one.
I think it's more for joining speed and wide table formats than sparse.
Okay, so that's all I want to say about the linear algebra unit. So let's move on to simulations. So the game plan here is we're going to spend the rest of today, probably all of Monday, and maybe that's about it. Maybe we'll go over a little bit into Wednesday. We'll talk about simulation. The main things I want to focus on in this unit are, one, to basically understand what a simulation study looks like and sort of how to think about it. And we're going to see a lot of that when we discuss the paper on Monday, but I'll do an introduction to it here and try and get us in the right frame of mind for being able to think about the simulation, the paper that we'll talk about. The other main thing I want to talk about is how does a computer actually generate random numbers, and what does it mean to work with those numbers in a repeatable way, and some of the details of the algorithms that are used for generating random numbers. And then we'll also talk some about if you have a distribution that is not easy to simulate values from that distribution, what are some methods that you can use, things like rejection sampling and importance sampling and some other methods. Okay, so what I want to do now is just talk about what would it mean to do a simulation study, or another term for this is a Monte Carlo study, and what is sort of the basic game plan that people follow when they do these sorts of things. And basically, in essentially any statistical paper where it's talking about a statistical method, there will usually be a simulation study to evaluate how well the method works. And you may also see this in papers in other fields that are not necessarily statistical journal papers. Okay, so let me try and motivate this as follows. So let's go back to a very simple statistical model, and we won't need to do a simulation study for this model, but the idea is to sort of motivate from the perspective of why we can do things in closed form here that we can't do in other situations. So suppose I have a data generating mechanism that's really simple. I just generate n different IID random normal variables, and they have a common mean theta and they have a common variance tau squared. So if I want to go ahead and estimate theta in this problem, right, everybody knows what that would be. Either you know from a statistics class what the answer to that is, or just by intuition you say, well, why don't I estimate the mean of this distribution, this population mean, with the sample mean, right? That just seems very intuitive. So, okay, so fine. So our estimate, theta hat of theta, is x bar, the sample mean. I'm going to write that as some function h of the full vector of x values. So this is just some functional of the data, and that's our estimator. Okay, so now suppose I've come up with this estimator in some way. Either I just came up with it off the top of my head like I sort of just did here, although obviously there's a lot more standing behind it, or I did a whole bunch of math to come up with what I thought was a good estimator for some unknown quantity in a statistical model. What you now want to do if you're thinking as a statistician is say, well, what are the properties of this estimator? How well does it perform if I repeated this experiment over and over again? So the idea of repeating the experiment is there's now going to be another sample size, not the n, which is the size of the data set, but what I'll call m, which is the idea that we're going to repeat this experiment m different times. I'm going to get m different data sets, each of size n, and I could use these m different experiments, these m different data sets, to evaluate the properties of this guy here, because I would get a theta hat for every one of these m experiments. Okay, I could do that. I could repeatedly generate m different data sets of size n and explore the properties of theta hat, but in this case I don't need to do that because of the fact that this is a normal distribution and this is a very simple linear function of the data. I can figure out in closed form that the expected value of theta hat, of this h of x, is just theta, so this thing is unbiased. Over repeated experiments, the average value of this thing is the true value of the parameter. And I can also figure out that the variance of this thing, the variance of theta hat, is tau squared over n, so it's going to scale with the number of points, of data points. And I also know in this case that x bar, h of x tilde, h of x tilde is normally distributed, so I know what its full distribution is. I could do other things that I don't necessarily need to be evaluating just simply the estimator itself. I might be interested in saying, what's the prediction error from this kind of model? If I use theta hat, i.e. h of x tilde, i.e. x bar, if I use that as my best guess for some new observation x star, I can figure out, well, this is just basically the mean square prediction error. This is the difference between my best guess and what the next observation that I might collect is, some new test observation. So the expected value of that squared is just going to be tau squared plus tau squared of n. I can work that out all in closed form because I know the distribution of n and because x bar has this nice simple linear form. Okay. So if things are simple, then I would just do this. I wouldn't need to do a simulation study. I could just do all this in closed form. I have the mathematical result, and I'm done. Okay, so questions about the setup, about sort of the initial part of the motivating example here? Okay. So one of the things you'll notice is that all of these things are expected values. Expected values are just integrals. This variance, of course, is just an expected value of something squared, as is actually, for that matter, this thing here. So in the cases where we can't do these integrals, we can't do these expectations in closed form, we can use simulation to basically approximate those integrals. And that's what a Monte Carlo study is. And we'll be using these Monte Carlo estimators. Okay, so now let me take this and sort of make a slight twist on this, which is suppose that instead of using x bar to estimate theta. Suppose I came along and I said, I'm going to take all the observations, I'm going to sort them, and I'm going to take the middle value of that thing. Okay? And I'm going to say that's my new estimator, x tilde. I'm hoping that this thing is a good estimator of this value theta. And I'm going to call this thing the median. Okay? So obviously other people have called this the median. But the idea of framing it that way was to go back to sort of step 0 of coming up with some idea for an estimator, and then we're going to evaluate how well it does to estimate the thing that we're interested in. And somebody might come up with a name for it as well, which somebody did back in the day. Okay, so now the problem is, for my x bar, which is the median, it's going to be very, very hard to work out what the expected value of x tilde is, what the expected value of the median is in closed form mathematically. And similarly, it's going to be very hard to work out what the variance of x tilde is, because it has this complicated form that involves the sorting and these order statistics and things like that. So okay, well I can't do these integrals in closed form in the same way that I could with x bar, but I can, because I'm in control of a computer, I can simulate data sets, and I could figure out what are the properties of x bar from simulating many, many data sets on a computer. Okay, so sometimes, I don't know, as in other things, it usually helps me to try and draw a picture of this, to try and sort of think concretely about it. So sometimes I'll sort of think about drawing this in this way, which is I'll be thinking about a matrix. This is going to be n, and m is going to index the different repeated samples of the different data sets I get. So for any given column here, I can compute x tilde. Maybe I'll put the 1 as a superscript. That might or might not be a handy thing to do. I can compute m different x tilde values. Right? Here are my m different medians from the case where I could repeat the experiment. Let's go back to this idea of what does it mean to have a p-value or confidence interval. It's all about how does it perform if I could repeat the experiment over and over again. So this, when I simulate data, I'm basically trying to replicate that situation, that I can repeat the experiment over and over again and see how well I do, as long as I can simulate data from some data generating mechanism or from some statistical model. Okay, so if I wanted to approximate, say, what's the variance of the median, I could do something like this with the m different x tilde values that I get from this set of simulated data sets. I could just take this variance as just an expected value of some squared quantity. So I could basically take the sample analog to that expected value across my m different simulated data sets. And I could say, what's the average squared distance between the ith median and the average over all of the medians squared? And this would give me a Monte Carlo estimate of what this variance of x tilde is. It's not going to be exactly what the variance is, because I've only got a finite sample m of the different data sets. But it should be a pretty close approximation if m is sufficiently large. Okay, so whenever you're designing a simulation study, so if you've gotten to this point, you've said, oh, I think this median might be a good way to estimate the original thing that I'm interested in, some theta from some distribution. And now I went to go and try and figure out how good an estimator it was of this quantity theta that I'm interested in. I now have to sit down and actually come up with what the simulation study is that I would then go implement on the computer. So if I were going to do that, what would I have to decide in this very simple setting in order to actually go and start sitting down and programming something? Okay, so what are some of the things I have to choose, Kelly?
You would want to look at your different sample sizes and whether or not you...
Okay, so which sample size are you talking about here?
Sorry, n.
Okay, so...
Well, full, but...
Okay, so let's go one by one. Okay, so I have to decide what my sample size is, first of all, right? I have to decide, I want to see how well this X tilde performs, but I'm going to have to decide, I'm going to have to figure out, I'm going to have to devise a simulation study and basically say, oh, well, this is how well it performs for a sample size of 10, or this is how well it performs for a sample size of 100, or for a sample size of 1,000. You're going to get different answers depending on what that n is. So I need to choose n. Or I need to choose a few different values of n, potentially. What else do I need to choose? Okay, so I need to choose the number of experiments or simulated data sets I'm going to do. So this doesn't have anything to do with the data generating mechanism, but this does. What else do I need to decide? Yanni?
How many times?
Okay, so that's the m. Is that what you mean? What do you mean by times? So if you were to, let's step back a second. Let's suppose we've chosen m and we've chosen n. And we now think about, we're going to go start to generate some data on the computer. What else would I need to choose in order to generate the data? In order to write some code to generate the data?
The distribution and parameters of the distribution.
Okay. So in that case over there, I said it was normal, but I might be interested in knowing how the median performs on some other kind of distribution. Right? So I'd have to figure out what's the distribution under which I'm going to generate the data, and what are the parameters of the distribution. So I'd actually have to choose. Well, if it were normal, I'd have to choose the theta and the tau squared. If it were some other distribution, there'd be some other parameters that I would have to choose. Let's see, is there anything else here? Yeah, so I guess that's, for this particular simple setting, I think that's probably all. Maybe I'm missing something. Kelly,
I have a question.
Yeah.
So when you say choose the parameters, do you have to dictate theta and tau squared, or could you generate a bunch of random numbers, fit parameters to those numbers, and then use your estimator based on this fitted model?
Well, we're basically saying the simulation study has the sort of conceit of saying that we control the world,
Oh, I see.
and we know how to generate, and we control how we generate data. So we would essentially always be choosing the distribution and the parameter values. But maybe responding to a slight twist on your question, we could, for example, have a real data set in hand and look at that real data set and come up with values of, well, we could come up with a distribution that seems appropriate for that data set. We could come up with a theta and a tau squared that seems appropriate for that data set. And then the idea is that our simulation study would be designed to evaluate how well does x bar do as an estimate of this parameter theta for values of the parameters and the distributional type that are perhaps relevant for our particular data set that we're interested in analyzing. Yeah.
So,
Yeah.
so here we generate different m sets of different data set, right?
Yeah.
So what's the difference on this kind of setting versus the bootstrap? Like we have one sample, one.
Yeah, so with the bootstrap, it's sort of the matrix of values that you would get would look like this. You'd have a data set of size n, the original data set. You'd bootstrap from it m different times and get m different resampled data sets. Then you would say get the value of your estimator for each of those, and you would then use that to evaluate to come up with a standard error or confidence interval for your parameter. So in some ways, it looks fairly similar, except in the bootstrap, you're taking the original vector of observations, 1 up to n observations, and using that to come up with the simulated data sets. In what I described here, without that, we're basically generating all these fresh from some underlying statistical model. But in some ways, it's sort of a similar kind of thing. Okay. Let's see, any other questions? Yeah, Eugene?
Well, isn't the problem the same as with any sample? Like, you have to make sure that n is less than calculation
Less than what?
10% of the population, right?
Sorry, I still didn't hear you.
Less than 10% of the population. You choose M as the doing it for a Bernoulli trial, right? You have to count for how many positive, how many negative.
I don't necessarily think that n has to be some fraction of m in this setting. I mean, there's no reason that n couldn't be 10 million here, and in that case we would be evaluating how well the median works for data sets that are of size 10 million. And we wouldn't need 10 million. We don't need m to be 10 million or bigger. We could still have m be, say, 500.
Yeah, but if you're doing n 10 million, and your population you're trying to simulate, the parameters will define it. It's a population that's less than a million, for example, then you're immediately oversampling the population.
Well, you're saying if you have a finite population that you're sampling?
I mean, for example, if you're trying to sample something about a population that's, say, the students taking a particular course.
Yeah.
There aren't a million students taking the course.
Right.
So if you simulate a sample size of a million, you're essentially sampling way more students.
Well, right. You would always, maybe I'm still not quite getting it, but your n should always be the right size relative to your real situation. So if I were trying to understand something about the behavior of some estimator of like the mean, well, this is a finite population, but if I went to estimate I'm not sure I want to go down the route that I was about to go down because I think it might just be confusing. But
What I was saying is that your simulation you're writing, you're playing God. Therefore, you have to be aware of what it is that you're simulating.
yeah, so you would carefully choose n. That if you were doing something where you in general your data sets were of size 30, then you would want to choose an n that was around 30 and see how well your estimator performs on data sets of that size. You wouldn't want to choose n to be 10 million because thinking somehow that having a bigger sample size is better. The right sample size is the one that's relevant for the size of the kinds of statistical problems or models that you're fitting.
Like I would choose bigger M.
Yeah. So then that's what we're going to talk about in a second. Is you can always make m bigger, and that's going to make your estimate of the expected value that you're trying to estimate better and better if you make m bigger. But making n bigger is not. N should be is sort of defined by the problem at hand. Yeah.
Yeah, in the non-parametric case where you're resampling from your original sample, your sample size is n. And so for the parametric case, when you specify the distribution with parameters, I think by convention you also have size.
Yeah, I mean, right. This where n comes from sort of goes back to what I was saying. Is it's sort of based on the kinds of sizes of data sets that you're generally analyzing. Okay, so then what's the idea of doing a Monte Carlo estimator? So I'm going to introduce a little bit of notation here. The reason I didn't use mu over there for the mean was because I wanted to use it here. So I'm going to define mu to be the expected value of some h of x. This h function is whatever I choose it to be. In this case, it was the mean. In this case, h of x was the function that creates the median. It's just some function, functional. And f is our data generating mechanism. In this case, I said it was a normal distribution with mean theta and variance tau squared, but it could be whatever data generating mechanism we decide on. Okay, and so the idea is that our Monte Carlo estimate of this expectation, basically this is a Monte Carlo integral here, is that my best estimate that I'll call mu hat is just the average of the h of xi's, where does h of xi come from? H of xi comes from taking the ith column of this big matrix, doing whatever the h function does to that set of values to compute sort of the margin value down here, which before was the median, and then averaging over all the different values that I've collected down here, one for every one of the fake data sets and simulated data sets. This thing is an average. I've sampled the data sets independently of one another. So this is just an average of IID numbers. So the usual statistical probabilistic law of large numbers says this thing converges almost surely to the true value of mu. And so the bigger m is, the closer this average is going to be to the true value mu, which is just the expectation that I'm interested in. So that's the justification for this. We can also compute what the variance is. And here, this is different than me saying I wanted to know what the variance of the median is. This is me saying I might want to know what the variance of my estimator is. So I could actually be thinking about, for example, if mu were the variance of x tilde, then and mu hat is that average there, then I could be interested in saying what's the variance of mu hat, which is the variance of x tilde. So there's sort of potentially two variances going on from here. This is the expectation I'm interested in estimating, the property of my estimator. This is my Monte Carlo error in estimating that thing. And as m gets bigger and bigger, this thing is not going to get smaller and smaller, but this variance of that estimator will get smaller and smaller as m gets bigger and bigger. So if we just go back to sort of simple properties of simple sums and averages, we can see that the variance of mu hat is sigma squared over m, where sigma squared is the variance of these h of x's, variance of h of x. And if I wanted to estimate this variance, well, I could just take a collection of these guys and try and estimate this. Well, an unbiased estimator of that would be to take 1 over m minus 1 times the squared deviations between the individual estimators and the average of all those mu hat. But then there's another factor m in here that comes from the fact that basically there's an m, and if I then put these two things together, this together with plugging in sigma squared hat for sigma squared, I get that my simulation error is estimated in this way, unless there are basically two m's in the denominator here. And that comes from the fact that I basically am first estimating the variability across these values, and then I have a 1 over m for the fact that this Monte Carlo average is just an average, and so the factor of 1 over m comes from the fact that I'm doing some averaging. So if I wanted to know how big m should be, I could compute this estimate, and I could see how big it was and decide if it was small enough for my purposes. And then if I needed it bigger, well, the nice thing about this situation, unlike most situations where we can't just go out and easily collect more data, is I can always go out and just, if I decide m isn't big enough, I can just go back to my computer and just generate more and more columns until it's sufficiently big that I've driven my error down, sufficiently small that I don't need to do any more simulation. Okay. So any questions about that? Yeah.
How do you compute the sigma hat?
How do I compute it?
Yeah.
So that's straightforward. As long as if I go back to here, what would I do? I would say, okay, I'm going to take each of my h of xi's. Those are going to be the values I get down here. Okay. I'm going to compute, well, and then I'm going to get mu hat, which is the average of all of those. Okay. So this is just an unbiased estimator of what the variance. This is just I'm just getting the sample variance of all these guys. Right. That's what this is. That's just the sample variance. So I could have called this s squared as well. And then I take that sigma squared hat and put it in the numerator here and divide by n. So then the result is that I've got the m and the m minus 1 in here.
So you don't use a Monte Carlo estimator to estimate the sigma hat?
No, this isn't. Well, this is essentially a Monte Carlo estimator because I am still relying on these simulated data
But
sets.
if you use a Monte Carlo simulation, they should be the 1 over m, 1 over m minus 1.
Yeah, it doesn't really matter whether you use m or m minus 1. M is going to be fairly big in all these situations because we control it. And so whether or not you choose to use this unbiased estimator or not, I mean, the fact that we're plugging in, we don't actually know what the true mu is, so we can't plug that in here, which is why I use the m minus 1. But it's really, I mean, substantively, it's really immaterial whether I had m or m minus 1 there. Other questions? Yeah.
What does linear chains mean in your side notes?
What does what?
In the side note?
Uh,
Misperception.
oh, this I probably
The
shouldn't.
chain.
Yeah, if you know anything about MCMC, there's you're doing something like this, but you end up instead of having independent samples, you end up having correlated samples, and so sometimes there's this idea that you might choose only some of them to get approximately independent samples. I probably should take it out because it's really just a distraction. So I wouldn't focus so much on that unless you already know something about MCMC and are interested in
That
that.
would be if the random number generator wasn't that random.
No, it's because MCMC, by the way it's constructed, generates correlated samples. Okay, let's see. There's a little bit I think I won't bother. This is probably not all that important to look into for our purposes. So let's talk a little bit about how we actually generate random numbers. Okay, so suppose we've gone back to the situation. We know we've come up with a way to generate our simulated data set. We know how to use Monte Carlo estimation to come up with estimates of integrals that we're interested in, of expectations we're interested in, like to estimate bias or to estimate variance or to estimate mean squared prediction error or things like that. So in order to do that, we need to actually be able to generate from our data generating model, our data generating mechanism. And in order to do that, we need to be able, in this case, to generate random normal numbers. Or maybe we had a more complicated model that involved gamma distributions and beta distributions or some other kinds of distributions. And for all of those situations, we need to be able to generate random numbers from the distribution of interest. Okay? So the question is, how do we do that? Well, ultimately, there are a whole bunch of algorithms for how you generate from a particular distribution of interest, but it all comes back to being able to generate uniform random numbers. If you can generate uniform random numbers, there are always going to be there's a slew of algorithms that says, okay, you give me uniform random numbers, I can give you back normal random numbers, I can give you back gammas, I can give you back t-distribution random numbers, et cetera, et cetera. So it really just comes back to how do I generate random uniforms. So the idea is that on a computer, we're not actually generating things that are truly random uniforms. We're coming up with a pseudo-random number generator that generates sequences of numbers that look like they're uniformly distributed and behave, hopefully for all of the purposes that we need them for, that they're essentially random uniforms. So the idea is that actually these random numbers that we generate are actually a deterministic sequence of numbers, and we just happen to pick off a chunk of them to do the calculations that we need to do. So the basic idea is, and it also turns out that these generators are all periodic. So you can think of this as we have a sequence of random numbers. I'm going to draw it from right to left. So these are the random uniforms that I'm generating. And so if I start here and then I need 20 random uniforms, I just take the next 20 in the sequence. These things are periodic, so it turns out that if we just kept generating random numbers for a very, very, very long time, I would come back to the point where the next one I generated would be this, and then this, and then this, and so I'd repeat the sequence over again. The period of this thing is very, very large. Like the standard R random number generator, the period of this is something like 10 to the 6,000, so it does take a very long time to come back around, but you would come back around if you had a lot of time. Okay, so the question is, how would we go about and generate a sequence that looks like this but behaves like independent random uniforms? So one way to do it is this thing, which is called the sequential congruential method. And the idea is, what you see is that it basically says, how do I generate the kth value? How do I generate this value here? Well, it says, take the previous values, apply some function to them, and divide by m and take the remainder. And the idea, the sort of motivation for this is if you think about taking large numbers and dividing by some other large number, and you look at the numbers that are sort of on the right-hand side of that number, they're in the remainder. If you look at them, those numbers look sort of arbitrary to us. And so the idea is that maybe those digits will behave as if they're basically random. And so this sort of procedure is going to give a number between 0 and m minus 1, because this is just taking the remainder. And so then if I wanted to convert that to a number between 0 and 1, I can just basically divide by m. So to convert the number that's between 0 and m minus 1, divide by m, that's going to give me a number that's essentially between 0 and 1. It's just a rescale. Okay. So a simpler version of what I wrote up here is this thing which is called a linear congruential generator, which is just take the most recent one, multiply by number a, take the remainder from dividing by m, then again divide by m to get to uniformity. So this thing is just going to be determined by what the values of a and m are. And And so an example of this, I'll just do a very simple example, and then we'll pick up with a more realistic example next time. Here's sort of the world's worst random number generator. So suppose this is U0, and this is U1, and suppose U0 is 2, and suppose I chose the value A to be 7 and M to be 13. So I'm going to take 2 times 7 is 14, divide by 13 and get the remainder, that's 1. So U1 is going to be equal to 1. Now I'm going to take 1 times 7, divide by 13 and get the remainder, that's going to be 7. So U2 is going to be 7. 7 times 7 is 49, divide by 13, get the remainder. If I keep going in this fashion and presuming that I haven't messed up the arithmetic at all, I will get this sequence of numbers, 13, 11, 12, 6. 11, 12, 6, 3, 8, 4. Now I get back, it turns out if I've got a 4 going in, 4 times 7 is 28, divided by 13 is 26, the remainder is 2. So I've gotten back to 2, and now if I keep going, I'll repeat it myself. So for this world's worst random number generator, the period is, it looks like 13 or so here. And this cycle, this would obviously come back around very quickly. But I could use this to generate random numbers. I just then take 2 divided by m. So my random numbers are 2/13, 1/13, 7/13, so on and so forth. Okay? And the other thing is, the idea of what a seed is if I wanted to be able to generate the same sequence of these numbers that are approximately random uniform over again, as long as I know where I started, this whole thing is completely deterministic. So if I knew, so in this case, I would say my seed is 2. That's my starting point. If I go back in and start with that same seed value of 2, I'm going to get the same sequence again. So I could set the seed and get the sequence. Or maybe in some other experiment, or maybe one of you is doing this, you're using the same generator, you decide to set the seed to be 5, well your sequence will start there and we'll move around and we'll come back to the same place eventually. So the idea of the seed is basically where you start so that you can reproduce things. And then what we'll see next time is that we'll get better performance if we have larger values of A and M, and we'll play out a more realistic example. So I will see you on Monday.
So like, what if
Hold on 1 second.